So far, we've talked about work being done by a constant force, and have defined work to be the component of that force in the direction of the displacement multiplied by the displacement. In equation terms, it's W equals F dot x. If we plotted out the graph of the force versus position, and we apply a constant force F to move the object from the initial position x1 to a final position x2, thereby displacing it by an amount x, then the work done, being the force times displacement, represents the area under the curve between the start position and the end position. It follows then that the area under any force curve as a function of position must also give us the work done regardless of whether the force is constant or not. So for a force that is changing with position, we can determine the area under the force curve by taking the integral of the curve. If we know the function of the curve, we can determine the work done by the force by integrating the force between the start position and the end position. If you've forgotten or unsure about what integration is, click on the link in the video. Remember that integration is the inverse of differentiation. Now let's have a look at a very simple example. Consider that you've got a force acting on an object. The force varies linearly with position and is given by the formula F is equal to 2x newtons. So how much work was done to move the object from its starting position at 2 meters to its final position at 6 meters, giving a displacement of 4 meters? Well, there's a few ways to go about it. The first simple way for this example is to calculate the area under the graph using basic geometry. We can see that the area under the curve between 2 and 6 meters is a trapezoid. A trapezoid has two parallel sides, h1 and h2, and a length between them, x. The formula for a trapezoid is equal to the sum of the two parallel sides divided by 2, then multiplied by the length. We can see from the graph that the height of the trapezoid at 2 meters is 4 newtons, and the height at 6 meters is 12 newtons, and the distance between them, which is the length, is 4 meters. So what is the area of the trapezoid? So putting these values into the formula gives us an area of 32 Newton meters. And of course, this is equivalent to the work done, so it has the units of joules. The other option using geometry is to break the trapezoid up into simpler shapes. So what we have is a rectangle with a length of 4 meters and a height of 4 newtons. So what's its area? The area under the rectangle is 16 Newton meters. And then we have a triangle with a height of 8 newtons and a length of 4 meters. So what is its area? So the area of the triangle is 16 Newton meters. Adding these two areas together gives us 32 Newton meters or 32 joules as expected. The last technique is to use integration. For integration, we start with a function for the force and integrate it from the start position to the end position. So we integrate the function 2x between the values of 2 meters and 6 meters. The integral of 2x is x squared. There will be a constant as a consequence of the integration, but we'll ignore it because we are only interested in the work done between 2 meters and 6 meters. The constant does not cause any displacement. Now we can solve for the integral by subtracting the integral solution at the start position from the solution at the end position. Graphically, this is equivalent to determining the area under the graph up to the final position and subtracting it with the area under the graph up to the start position using geometry. So what is the area of the shaded triangle under the curve up to 6 meters? And what is the area of the shaded triangle under the curve up to 2 meters? So the area up to 6 meters is 36 joules, and the area up to 2 meters is 4 joules. Subtracting 4 from 36 gives us an area of 32 joules as expected. That is, it took 32 joules for the force to move the object from 2 meters to 6 meters.